Welcome to lecture 10 on structural analysis 1. So in this lecture we are going to start the unit 2 slope deflection method. So this is the unit 2 slope deflection method syllabus. So first we are going to see the introduction to displacement method, that is what is slope deflection method. Next we are going to see what are all the assumptions made in slope deflection method, and next what is mean by fixed end moments and what are all the sign conventions used particularly for this slope deflection method. And we are going to see the how the slope deflection equation, how to write a slope deflection equation. And next we are going to apply the concept of assumption, fixed end moment, sign convention, slope deflection equation to the continuous beam problem, simple frame problem, and portal frame with and without sway problems, and support settlement problems. So support settlement means the support settlement will occur in the beam, frame, and portal frame also. In portal frame means which is subjected to the horizontal sway, that is horizontal motions. We will have portal frame in horizontal motions in portal frames. So first we are going to see about the introduction to displacement methods. So in this particular lecture we are going to see about the concept of displacement methods. First of all, we want to know what is the course outcome of this particular unit. That is, we are going to learn how to calculate the bending moment and shear force using the slope deflection method. So the specific outcome of this lecture is we are going to see what is displacement method and what are all the assumptions made in the slope deflection method, and we are going to see how we are going to calculate using the slope deflection equation. That is, it includes equation, sign convention, and what is meant by fixed end moments. These are included in slope deflection equation. So I have taken the reference for this lecture is Structural Analysis Volume 1 book by Dr. R. Vaidyanathan and Dr. P. Perumal from page number 48 to 50. So first of all, we are going to see what is slope deflection method. This method is used to analyze the indeterminate structures. So what do you mean by indeterminate structures? If you see, we have seen determinate structures, that is deflection of determinate structures in unit 1. So the difference between determinate and indeterminate, first we need to understand that. So determinate structures means a structure can be analyzed by using the equilibrium equations. So what are all the equilibrium equations? Sigma h equal to 0, sigma v equal to 0, and sigma m equal to 0. These three are the equilibrium equations. So indeterminate structures means the structure cannot be analyzed by using these three equilibrium equations, and we need some more equations to solve the structure. Then that structure is known as indeterminate structures. So the differentiate between determinate and indeterminate structures may be asked as a 2 mark. So the main aim of the slope deflection method is to analyze the statically indeterminate structures. So first of all, we want to find out what is the slope at a end or slope at a point and what is the relative displacement at that point. Then we can find the moment. So our main aim of the unit 2 is to calculate the bending moment and shear force. So in order to calculate the moment, we need to first of all we need to find out the what is the slope at the point and what is the displacement. So if we know the slope and displacement, then we can express the moment in terms of slope, deflection or displacement, stiffness, and length of the member. So if a structure is made up of several members, then we need to apply the slope deflection equation for each and every member of the structure. And by using appropriate equation of equilibrium of a joint along with slope deflection equation, we will calculate or we will obtain a set of equations with displacement as unknown. So by solving that equation, we can calculate the displacement. If we know the displacement, we can calculate the slope as I have mentioned in the point 2. So with the displacements calculated, that is what I explained in the last point. With the displacements evaluated, the end moments can be computed using slope deflection equation. So in slope deflection equation, we need to mainly find out what is the slope and what is the displacement. So by calculating these two, because the name itself indicates that slope deflection. So based on slope and deflection, we are going to find out the moment and shear force. So what are all the assumptions made in slope deflection equation. So the first and foremost assumption is all the joints are rigid. That is, if a joint is having a 90-degree, then after all the bending, or after even after undergoing all the changes, the joints will remain rigid. That is, the angle between the members of the joint does not change. That is, if it is 90-degree, then it always remains 90-degree. Even after bending also, it will maintain 90-degree. So second assumption is, whenever the beams or frames are deflected, the rigid joints are considered to rotate as a whole. That is what I have explained. If it is 90-degree and if it rotate like this, then also it will have a 90-degree angle. So distortions due to axial and shear stresses being very small are neglected. So the distortions and due to the axial, that is, distortions means changes or deflections or deformations due to the axial or shear stress being very small, because we will consider those are small and we will neglect it while calculating the answers. So next we are going to see the sign convention. So moment at the ends of the member. Generally we will always assume that the clockwise moment is positive. That is, as clock, how the if the moment rotates like a clock, then the moment is positive. If it is anti-clockwise, then it is negative. Rotation. Rotation means the joint rotation. Even for joint rotation also, if the clockwise rotation is there, then we will consider it as positive, and if it is anti-clockwise rotation, then it will be considered as negative. Next is sinking. Sinking means, we know that sinking means going down. So some problem we will have a condition that the frame, if a frame is there, then one support will hold in position, other support will either go down or go up. So if the right support goes down with respect to left support, then the supports, moments on the supports will be considered as negative. So remember this, if the right support is below, then it is downward direction, then it is negative. If the right support move in upward direction, that is in move upward direction, then the moment on both supports will be positive. So consider, we will always use the sign convention based on the right support. So if the right support is going downwards, then it is negative. If it is upwards, then it is positive. So remember, this sign convention is applicable only to the slope deflection method. So next, what is fixed end moments? For a beam, if you take a member and if you apply the transverse load, I think so I have already explained what is transverse load. Transverse means that we apply the load perpendicular to the axis of the member. So for a transversely loaded member at the ends, moments are developed. Generally we know that fixed end moments means the moment which is developed at the fixed end, that only called as fixed end moments. So how it is generated? If we have a fixed member, that is a member is fixed against rotation and displacement at a point, then there we will have the fixed end moments. If you see here, they have mentioned that for a transversely loaded member at the ends, moments are developed when the ends are fixed against rotation and translation. Translation is nothing but the displacement or movement. So it may be determined by any of the standard methods of indeterminate analysis. Generally, we will calculate the fixed end moments by using the formula, the fixed end condition. If the beam is fixed, then the moment is calculated by using WL square by 12. So we will see that in detail way in our problem. So we are going to see what is the slope deflection equation. So the slope deflection equation give the support moment of a member in terms of slope. That is, we will explain in slope deflection method, we will calculate the moment based on slope, deflection, stiffness and length of the member. So we are going to see what is the slope deflection equation. So if you see in this drawing, if you see in this slide, we have a drawing and we have some writings. So these statements will be based on the drawing. So if you see, this is what I have told us. If the beam is fixed, then we will have a fixed end moment, that is moments at the support, that is nothing but this MFAB and MFBA. These two are called as fixed end moments. Next, if you see if the member has a rotation, that is if a member is allowed to rotate, then we will have a moment, that is we will have some value as 4ei theta a by L. So at the joint, at the point where the rotation is allowed, then we will have 4ei theta a by L. This rotation will have an impact on the other joint, that is half of the impact will be there, that is 2ei theta a by L. So if you see here, we are having a rotation theta b at the point B, then we will have the value as at theta, sorry, at B we will have the value as 4e theta b by L. At A we will have the impact, that is half of this value will come here, that is 2e theta b by L. So if you see here, we are having a straight beam and it is sinking, both the ends are sinking, that is A is moving by delta A and B is sinking by delta B. So if you see here, delta B is in upward direction, so it is positive. So this value can be calculated by using the condition 6E8 delta by L square. So here if you see delta equal to delta B minus delta A. So it is moving upwards, so the deflection is positive. So next, how we are going to express the, or how we are going to represent the slope deflection equation. So we need to find out the final end moments. So first we need to find the fixed end moments due to the external loads. That is, if you see in this diagram, we are going to first find the fixed end moments. F of MFAB is nothing but the fixed end moments at A, and MFBA is fixed end moment at B. Next, we need to find out the moment due to rotation at A. So, what is the moment induced due to rotation at A? That is, if you see here at A, we are having 4E theta A by L, and this will create a half of the impact on the other end, that is 2E theta A by L at B. So, next we need to find out the moment due to rotation at B. So, the moment due to rotation at B also will generate the same impact. Remember, when we are applying a rotation to a point, at that point we will have 4E theta B by L, and at the adjacent side, that is near to the nearest point, we will have half of that impact. So next, the moment due to differential transverse displacement of B above A. So if you see here, B is moving above A. So for that we are going to use the condition 6E delta divided by L square. This is the formula to calculate the displacement, that is sinking. So in order to calculate the moment AB, that is moment in the section AB or member AB, we are going to use this condition. We are going to add all this, that is MFAB plus 4E theta A by L plus 2E theta B by L and 6E delta by L square. So if we are going to find out for MBA, that is moment BA, that is first MAB means at this point we are finding the moment, BA means at this point. So if you apply that, then the formula will become MFBA plus 4E theta B by, sorry, yes, 4E theta B by L plus 2E theta A by L plus 6E delta by L square. Because if you see here, we need to consider this point while calculating for MBA, that is moment at B. So we need to add MFBA plus 2E theta A by L plus 4E theta B by L plus 6E delta divided by L square. So we need to consider that condition. So if I take I by L as stiffness K, because I by L is nothing but the stiffness K, so we will substitute the value here. So MFBAB plus we are having 2 common in all terms, so we will take 2K, that is 2EK, because E is also common. I by L is nothing but we are assuming it as K. So 2EK, 2 theta A plus theta B plus 3 delta by L. So if you see here moment at B, so I have already mentioned that MFBA plus 2EK theta A plus 2 theta B plus 3 delta by L. So this is the formula, this is the way, or this is the final slope deflection equation to find out the moment at A and moment at B. Next, we are going to see what are all the applications for this slope deflection equation. The slope deflection equation is applied to the following structures, that is continuous beam, simple frame and portal frame. So we are going to apply the slope deflection equation for these conditions for our unit 2. So continuous beam, simple frame and portal frame. Portal frame means the frame which is subjected to movements. So this is the general introduction to the slope deflection equation. In next class, we will see a slope deflection equation application on the continuous beam problem. If you have any doubts, feel free to contact me.